Hi, I'm Ed Gehringer from NC State University. Our paper is Transfer and Active Learning for Problem Detection. This is work done jointly with some of my students at NC State, my colleague and former student Yang Song from University of North Carolina at Wilmington, and some of our interns from the Beijing Institute of Technology. The term peer assessment means students reviewing each other's work. It became a common practice in classrooms in the 1970s and moved online beginning in the 1990s. Peer assessment has many advantages. It can provide students with more formative feedback than they would receive from the instructor, and they receive it more quickly. Perhaps the greatest benefit is that the process of writing feedback forces them to think metacognitively about the assignment, which deepens their understanding of their work. Peer assessments are only useful to authors if they help them improve their work. Toward this end, reviews should detect problems in the draft and make suggestions for how to improve it. Reviewers need to be given an incentive to submit good reviews, so we would like to be able to automatically measure review quality. We have been using NLP and machine learning techniques to recognize when reviews contain suggestions, as we reported at last year's EDM conference, and when they detect problems, as described in a poster at this conference. To recognize suggestions and problems, we coded thousands of review comments taken from reviews in a computer science course and applied machine learning to automatically detect those features in other reviews. We hope that our machine learning algorithms will work, not just for computer science reviews, but also for reviews in other disciplines. In this paper, we test whether our machine learning approach can successfully detect suggestions in reviews given for a course in a college of education.
Now, I would like to give you a very brief background. There have been several attempts to apply NLP techniques and machine learning algorithms to automating various aspects of review assessment. However, parallel research on applying NLP and machine learning to peer review has been limited in scope. This paper focuses on detecting problem statements in a domain using reviews labeled for another domain. Our work concurs transfer learning. With traditional machine learning algorithms, the training data and the test data must be in the same feature space and have the same distribution. We investigate using data labeled in one domain to detect problems in another domain. The transfer learning approach used in this paper is called the parameter transfer approach, which is a simple but effective method for transferring knowledge by sharing parameters. An assumption of this approach is that the knowledge can be encoded into and transferred across tasks by those shared parameters. Active learning is a subfield of machine learning where there is abundant unlabeled data, but their labels are difficult, time-consuming, or expensive to query. The algorithms are allowed to interactively query a human annotator to label new data points chosen by a predefined strategy. The key hypothesis is that the learning algorithm would perform better with less training if the algorithm could determine which instances are most informative.
Our research task to explore the effects of active learning and transfer learning involved 4 datasets. 2 of these originated from academic sources, while the other 2 involved hotel and Amazon product reviews. We used the first 2 datasets for the active learning experiments coming from the expertise system, and we used all 4 datasets for the transfer learning experiments. The expertise system is a web-based education platform instructors can use to distribute homework assignments and team projects. The key feature of this platform comes in later stages when students submit their work, where they assess the work product of other students by giving a numeric score as well as a comment to justify their decision. For team assignments, students would assess work done by other teams as well as the contributions of their teammates. The computer science dataset and education class datasets were derived from this expertise system. For the computer science datasets, we had teams of students all manually annotate other teams' peer reviews for projects in the class, where we decided to keep all the observations that had unanimous labels as containing a problem statement or not containing a problem statement. Similarly, the education dataset contained observations from the expertise system. However, this is for longer written papers instead of shorter projects. The big difference is this was unlabeled data, so our research team had to manually label the data, where we decided to take the observations in which all of our team members decided to label the same. This helped ensure that the comments did actually state or not state a problem in the author's work. For the Amazon and hotel reviews, the original data had a sentiment score in a continuous form from 1 to 5, as in worst to best. And we found through manual inspection that the lowest rated reviews all had problem statements referring to either the hotel experience or the product review. Also, for the best reviews, we found that there was no problem. From this, we were able to take the lowest and best rated hotels and Amazon products and relabel them as 0 or 1 as not containing a problem statement or containing a problem statement. This is how we had similarly labeled datasets to use for the transfer learning task. Now, all of the data underwent the same data preprocessing. So the first thing we did was remove all punctuation aside from sentence and period marks. We removed other necessary information such as special characters and numbers and URL links. Furthermore, we decided to downsample the majority class in terms of labels in order to make sure that this dataset was balanced. This helps models such as naive Bayes in order to help predict observations based on their features and not just class proportion. Other methods we used for comparison purposes was lemmatization and stop and burden removal on the basic clean text. Now for the models, we used logistic regression, random forest, naive Bayes, and support vector machine. We decided to do this to compare the models' performance with each other and to determine which model performed the best for our tasks. The full dataset was used for training when other datasets were used for testing during the transfer learning process. And in order to form a baseline performance, when training and testing on the same dataset, we used a 90-10 train test split.
At the beginning of this experiment, we wanted to see that if model knowledge could be transferred between domains. What we did first is that we validated transferring indeed has happened between models built on the hotel review dataset and an Amazon review dataset. We trained a model on the hotel review dataset and used it to complete classification tasks on the Amazon review dataset. Then we attempted transferring between our computer science dataset and the models built on the 2 datasets we previously mentioned. Lastly, we annotated 100 entries in the education dataset to test if knowledge could be transferred into that. In the next slide, we'll talk about results of these experiments. In previous experiment, we could see that models trained on one dataset could still preserve some performance when tested on another, yielding an F1 score much larger than 0.5. This has validated our prior belief of knowledge transfer between domains. What we did next is to observe if text preprocessing would do any difference in the transferring process. As could be observed, lemmatizing does not provide significant advantage in terms of how well knowledge is transferred. But on the other side, stop word removal certainly has hindered model performance. This is potentially caused by losing some, if not all, of the auxiliary verbs when stop words are removed. These auxiliary verbs, such as should have, could have, are crucial when looking for problem statements. To improve model performance after transferring, we implemented some active learning methods. Our experiment focused on performance of transferring model knowledge from the computer science domain to the education domain. The process involves having each model select the subset of most uncertain entries, which are those with low confidence score in prediction. For human, aka Oracle, to label, then to fine-tune with this additional information. In the fine-tuning process, we used model scores using the original train and test observation as our baseline, and compared it with model performances when we have trained data augmented by a small subset of uncertain entries, labeled by Oracle in education dataset for each model, respectively. Lastly, we merged these newly labeled entries, then augmented trained data with it, later tested against it. In the next slide, we'll talk about results of these operations.
as could be observed between the blue and red bars. Each model received some improvements when fine-tuned with additional information towards their uncertainties. When we combine all of the models' clarified uncertainties and serve them to the models, they receive the maximum benefits in terms of model performance, evaluated with F1 score. As a conclusion, transferring model knowledge from one subject to another is certainly feasible, but at the cost of losing some precision. It works the best between similar domains. In the end, doing active learning with uncertainty sampling could certainly help regain some performance for models with a relatively inexpensive cost. This is the end of this presentation. If you have any question, please feel free to ask now.